seem to be figuring out this really strange bug that I hit in OBS almost every time I start the stream. It looks like if I switch the profile that I have it set to, like which collection of, streaming settings, it looks like if I switch that away from and then right back to my usual one right before I start the stream, it looks like it works out. If I just start the stream, then it gives me a nonsense error, which persists until I would usually switch to a different profile and then back as a workaround. But anyway, it seems like the workaround on its own has the effect I want, and it might just be timing related, so it makes me really curious about the nature of the bug. Anyway, that was a bit of a rambly way to start this, but hello. This is another work in progress stream coming at you from a still pretty sunny Friday afternoon over here. And this is another kind of procrastination stream, so this is not really furthering the ongoing projects. It's just something kind of random that I thought was interesting and worth sharing. So this one is actually me satisfying some curiosity and trying to dig through what's going on inside this this AIY Vision kit that Google has been that they recently released, and you can get one. So I don't actually have one of these kits though. I've just been really curious from seeing the released information, from seeing some other people review it, and so I thought I would just take an opportunity to talk about that a little bit on this stream and dig into the information that's been released about that. Tuco was in perfect frame, and then he wandered over here to hang out with me. Oh, where is he? Oh, he's right here behind me. He's actually pretty close to the bot. When I pay attention to driving the bot carefully, it actually does reasonably well as a camera. I'm sure it'll be better once I have some kind of active compensation for that pendulum swing. Okay, he just completely stole my seat right now. That's fine. I can just stand right next to the microphone and slurp my coffee. How is everyone's Friday afternoon? It's been a weird week. I don't know, how's your week been? I feel like for me personally, I feel like I haven't gotten much done just because of just personal stuff and just random depression and, all that. And then, if you're unlucky enough to be following the news, then the news has been pretty intense lately. I should probably avoid it more. It's also just, I don't know, I've got a close friend that I like to hang out with, and they've been really busy at work this week, so I've been away from them, which has been a bit of a bummer. I've had Tuco. Tuco's been more bossy this week lately, which has also been... It's like Tuco knows that I'm having a rough week already, and then he just wants me to play continuously, which is good to some extent, but when he's super bossy about it and just wants me to play constantly, it doesn't necessarily help. Aw. Mark says they're glad it's Friday afternoon. I spent most of the day debugging something that reduced to authentication failed. Expected token 12345. Got 12345. Yeah, that sounds frustrating. Yeah, thank goodness it's Friday. Lilia's on YouTube chat asking what's new. I guess, stuff will continue to be new, especially as long as I'm starting new projects all the time. We've had some really interesting hardware in the mail recently. I should actually just do an edited kind of mega wrap-up video of many of the unboxings recently to introduce the non-streaming edited video kind of crowd to the delightful reverse engineerables that we have at the moment. So yeah, that's something that I really want to try to fix. Is right now I feel like there's a big gap between the experience people are getting if you happen to be able to tune into these streams pretty regularly versus if you tune in occasionally versus if you don't watch the streams at all and just watch the edited videos. So yeah, maybe I don't know. I've been really trying to take this particular batch of Tuco Flyer footage and kind of squeeze out all of the edited videos that I want from it so that I can discard the footage and make some more hard disk space. But it might be worth taking an aside from that and just making some more self-contained videos as well. So, yeah, and today is, today's a momentous day for a lot of students, and there's a lot going on. Anyway, so like I was saying, today's stream is sort of avoiding everything. It's just completely random. This one started from just me seeing something on the internet and wondering what else is behind that. So this might be a bit of just a bit of a journey together while we try to satisfy some curiosity about what a particular product actually is. So let's make sure I'm monitoring the audio here so that it's an acceptable volume. Oh, there's so much echo in this, and I think a lot of the echo is in the original recording, but then my volumes here are super low. I think the audio from my emulator on the last stream was actually really, really hot, just like the levels were high, so I had the gains all turned super low. Yeah, negative 25 decibels. That's maybe excessive. Let's try this. As usual in the stream, we are debugging the AV setup as it happens, doing it all live.
You've got the contents listed on the back here as well, so you don't have to keep like looking up.
Yeah, okay. So this is what I wanted. So this is one of the things that I saw. I'd seen some people demoing this AIY Vision kit, including this video on Hackster. And I watched this one, and this was a pretty good just walkthrough of the end-user experience that you can expect with this thing. And so I don't want to, like, gank her audio content here. If you're interested in this, you should definitely watch the original video. I just wanted to reference this as a thing that I experienced and caused me to appreciate the walkthrough, but it also raised a bunch of questions about what else there is for makers. So right here you can see that this kit's pretty interesting. It's got a Raspberry Pi Zero. I'm going to try to actually get in frame here. Tuco stole my actual seat, but I think I can move another seat over here. Alright, we got kitty cam. This hat is covering up my ears, which makes kind of my perception of the environment a little bit strange. Oh yeah, that's a good question. Aiden's asking how the YouTube channel has been working out since splitting the streams off from the main channel. Yeah, I should actually check the stats on that because it's been probably like a week or two since I looked at it. But last time I looked at it, it seemed like that was helping. Like, it seems like there's a contingent of people who enjoy the edited videos, but just don't want to be constantly bothered by the release of all the live streams and their archives. And so, yeah, there's this constant kind of jitter around 0 where I would get these spikes of new subscribers when I release something new, but in between releases, then there is, I think there was still a net positive, but there were just a lot of people unsubscribing, just going up and down. And I don't think the stats that YouTube provided me told me exactly why people were unsubscribing. Not that it knows, but like I don't think it told me like what the context was, like whether it was like they just watched a video they didn't like, or whether like they just were randomly scrolling or whatever. But the the pattern where it just seemed to constantly be happening regardless of my release schedule just seemed to imply to, or regardless of the edited release schedule, seemed to imply to me that it was tied to the more frequent releases of my live streams. So I couldn't really test that as far as I could tell without actually moving the live streams. And so in light of that, yeah, last time I looked at it, it seemed like, from the noisy data I've got, that it's, that like trend below 0 is no longer happening. There's still a non-zero number of just like random unsubscribes when I'm not releasing anything. So I'm assuming that some people must either just get randomly recommended the videos and then be like, oh, I can't believe she also made this, unsubscribe or something. Or people are just like randomly unsubscribing from people. I mean, I don't know. People do stuff on the internet for all sorts of reasons, right? But as far as like the perspective I have trying to understand how to help people have a better experience with the content that I'm releasing, it seems like this is an improvement. There still aren't a huge number of people on the live stream channel relative to the main channel. I think last time I looked there was something like 14,000 subscribers on the main channel and not quite 1,000 on the live stream channel. But then I've also been seeing a lot more people subscribing on Twitch now that I think more people know I'm also on Twitch. So I'm not really that fussed about getting the largest numbers or anything on any of the platforms, as long as it makes it sufficiently easy for people to actually find the content. And so that's this question of like, how does this even work? How do people ever even find this stuff? What are people even looking for? And I'm still pretty new at all this, and I'm certainly not like a social media professional or anything, so I'm still trying to figure out how to do this also. But as far as I can tell, the split seems to be beneficial so far. So this kit's pretty interesting. It has, I think it comes with everything included. I know I could actually just like walk to Target and buy one of these and show you basically the same experience, but I guess the questions that I had started to lead me down this path that didn't even really require having the hardware in my hands to start answering those questions. So in this, she's putting together the Raspberry Pi Zero, and this is, it's called the Vision bonnet, and I don't think any of that is open source. So the Vision bonnet has this system on chip from, well, it was originally a separate company, Movidius, and they got bought by Intel. So now Intel has this branded Movidius chip, which it turns out is actually a Spark processor with a bunch of very long instruction word, like VLIW, coprocessor units that you can just like run a whole bunch of these in parallel to do. I think they're specialized for like half-width floating point or something like that. It looks a lot like a GPU, but it's basically specialized to run neural networks and stuff like that. Anyway, that's the board that they're giving you here. So let's see if I can point out the relevant parts here. So this flat flex is actually plugged into the camera port on the I think it's the camera port. Is that a camera port or a TFT port? It's something that you can run like a MIPI bus over. So it's a digital video bus. And I don't know exactly what they're using this for, but I assume that they would want to be able to perhaps forward the video stream both to the the coprocessor and to the main Raspberry Pi for like compressing it and saving it. Maybe you can like overlay stuff onto the stream and then send it out. It seems like the coprocessor is actually pretty versatile with how it can use the MIPI interface to send and receive video data, but I don't know specifically what they're using it for in this application. Why did you just lock? Have I been not touching it for that long? That's interesting. I have another computer connected to this with a remote desktop. I wonder if that one went to sleep or something and then forwarded a sleep signal. Yeah, so there's a stack of these 2 layers now. There's the Raspberry Pi, there's this Vision bonnet. Did we miss the good shot of a Vision bonnet? Anyway, we don't need to like screen scrape everything from this particular assembly. There are actually like product photos on their website and everything, but okay, that's the Raspberry Pi. And this blue thing is the Intel Vision board. So there's a Raspberry Pi camera here. So the board is wired sort of like a pass-through with the camera connecting on one end, then it connects back to the Raspberry Pi's camera port. So they might have just had this wired so that you can use it as a regular Raspberry Pi camera, but then you can also do co-processing on it. So anyway, it comes with this cardboard case. Basically, this entire process that they've set up for the end user is like, it's supposed to be like a do-it-yourself kit, but as far as I can tell, the do-it-yourself experience is mostly folding cardboard, which I don't know if that's intended to be the main extent of it. I mean, I'm not knocking the cardboard. I think the cardboard is kind of cute. Like, I think it's got some advantages over plastic in that it's you know, more economical and in fact easier to customize, and maybe people will treat it as less precious and more customizable and hackable. So I think the cardboard has some benefits, but I guess my question with this was then, well, what is this really intended to offer the DIY person? Like, if you are buying this with the intent of having a do-it-yourself artificial intelligence experience, which part of it is actually do-it-yourself? And that was the question I wanted to answer. And so they've got 2 kits. They've got one that's focused on audio, one that's focused on vision. The audio kit, as far as I can tell, I have not looked closely at it because the vision one was the one that kind of caught my interest first. It looks like the audio kit, this board might just be some like GPIOs and an audio amplifier. I don't think it does any processing. I think this is, as far as I can tell, this is all doing the processing on the cloud, same as if you were to like try to turn your Raspberry Pi into an Alexa or something. So I haven't looked closely at this, but I suspect that the hardware is not especially unique here, and that it's mostly just acting as a platform to run some code that talks to the cloud. There might be some local processing here, like there might be a local like wake word detector running, but I haven't looked closely at that. And then the Vision kit is actually doing all the recognition on board. That was part of what was interesting here, is it's like, oh, it's a Raspberry Pi and it's running these neural nets, what are they doing here? And they do have some custom hardware. So what is the experience here? This is what I'm wondering. Like, I mean, I know if I were to build a neural net to do something useful, there are a bunch of different abstraction levels you could start with. So you could do the kind of most easy thing to do on a modern desktop or laptop these days, which would be to probably download you know, one of several great Python or JavaScript frameworks to do neural nets, and they will have already implemented all the GPU acceleration, you know, and then your GPU itself already, of course, has drivers and firmware and everything else. A lot of that is already kind of sealed off from you just by virtue of being closed source and or extremely complex. But you know, most of the neural net frameworks that you'll see out there in the real world are, at least in the ways that are interesting for most people doing this kind of research, open source, even if they rely on levels underneath that you can't get access to. So So I was just kind of curious, like, how much of this is actually open? Like, where do they draw those abstraction boundaries? Because if you look at this on, for example, the neural net I'm using for TucoFlyer in the box right down there, that one, the source code at pretty much every layer that is relevant to this application is completely open, which is to say that all of my code for the robot is open source, the neural network architecture, the runtime, the training code, all of that is open source. But then it's built on top of CUDA, which is not open source, and then CUDA is, of course, requiring this massive silicon and firmware infrastructure and driver infrastructure from NVIDIA, which is, of course, not open. Theoretically, you could take that specification for CUDA and then build something underneath it that has a similar effect. But, you know, so it's common for us to already be dealing with these different layers where we have to kind of pick something where it's hard to get much further below that. It's especially frustrating with stuff like GPUs. For CPU-only applications, there are plenty of open source examples of CPUs or entire machines that people have built from scratch. But doing that with any kind of approximation of modern scale or speed or power efficiency just requires all of this Silicon Foundry stuff, which is also completely not open right now. Because just the library files that define like what a transistor looks like or what standard logic cells look like or what their electrical properties are, like those files themselves are actually, you know, for the most recent processes at least, those are like the crown jewels of the trade secrets, and you know, you're not going to just find those online. You'll find much older silicon processes, but so I'm just curious, like where does the customizability go here? The cardboard is maybe a good start, and like, you know, I encouraging people to hack on this, and so I'm curious where it goes. And that got me curious about what the interface between the Raspberry Pi and the GPU board is like, how much of that is open. So yeah, they're talking about how to get this set up. Basically the same steps we just saw. This comes with a pre-programmed SD card, but I also found a forum post where they just had a link to the image on the AIY project site. Where was that? Oh yeah, a GitHub issue on the Google AIY projects. So yeah, here they had a link to some images just directly on the Google site. So, you know, I didn't see anything more obvious about where the rest of the components in this image come from. So, you know, right away, this repository here, AIY projects Raspbian, came up when I was searching for like where the source code for this might be. And so this has kind of system setup stuff. So this contains an easy-to-use API for the Vision and Voice Kit. So what's actually in here? There's this AIY directory with the libraries. There are examples. And all this stuff is installed in the Raspbian image when you get this kit. So you follow the instructions, you put the kit together, you boot it up, and then you can run these Python programs or write your own Python programs. And that's kind of the intended place to direct. So like there are a bunch of on-ramps. I mean, I like this approach where you have a project that might appeal to people for many reasons, and then you give out several different kind of on-ramps and off-ramps for getting interested in the project, but also perhaps reaching an intermediate goal with the project. Like having assembled something and then having an interesting assembled thing is a nice intermediate goal, and maybe you let people, you know, kind of leave the project there for a while and then come back to it, or maybe you give people the opportunity to immediately go forward and, you know, do something more custom with it. I mean, I like that approach. So I don't know, the built-in models have some like kind of weird stuff. Like the first one they listed was like an affect classifier, which is just, I find like that's really far on the creepy side of applications for this stuff, so it's like kind of weird that that would be your first example. But then there's also like, what kind of food is this? There's a dish classifier here. So these are just like shell launcher kind of things. I think the actual code is in some other place. Yeah, AIY Vision models. So they put the models into the library, so they're easy to reuse in other programs. So the intent is one of those off-ramps now is like, I want to write custom Python code, but I don't necessarily want to make a custom model, so they give you a way to do that, which seems nice. And I think this is all based on TensorFlow. I think MobileNet is a smaller architecture that's inspired by ImageNet, but I don't actually know for sure. Yeah. All right, so these are specific to particular computer vision models, neural network models even. And then this vision directory interested me. It has some interesting stuff here. So what is the annotator? Okay, cool. So there is a way of drawing on top of the image as it passes through from the camera's interface cable into the Raspberry Pi's camera interface. So that's pretty neat. This is actually a lot like how I ended up setting up the computer vision OBS plugin for TucoFlyer. It kind of acts like a video pass-through that also draws annotations. The video board also has its own GPIOs. They added just some extra PWM and some analog inputs, which seemed kind of neat. So this is I think an obsolete interface for that, but they do have an interface for that somewhere. I think they moved it to the PyGPIO library. Yeah, and those are the models we were just looking at. So anyway, proto. What's going on in here, right? Protocol buffers. So, and then I started looking for this protocol. So I'm not an expert on protocol buffers, but the basic gist of this is here that it's a serialization format, much like something like JSON or a Python pickle, I guess. But it's designed to be very space and time efficient, and it's designed such that the specification for what the data format is not part of the data. There's a separate description. You have to know what the format you're expecting is, and then you can parse it. But this is interesting. So this is actually, this is the API boundary. We're finally finding the layer that sits right between the open source portion of this project and the very proprietary part of this project. So this is using a Python protobuf library. This whole file is automatically generated, but I don't think the source code for the protocol buffer generator has been supplied here. So I don't think we actually have the whatever the like .proto file. I think we just have the generated Python, which is kind of annoying. But by reading this, we could figure out what the protocol is. So you can see that the name of the protocol is Spacepark.vision. As far as I can tell, the Spacepark thing is the code name for the Google project, where Google is porting basically a TensorFlow runtime to this Movidius project processor. So these two names started coming up. So there was Spacepark, and then Myriad. And so Myriad, it turns out, is the actual processor. It's the particular generation of the Movidius. Movidius originally was the name of a separate company that developed all this technology. Then Intel buys it. Now Movidius is just now effectively a brand name for this generation, or this line of processors. And the Myriad, so actually I don't know what the difference is between the Myriad 2, the Myriad X, and the original Myriad, but everything with the name Myriad in it seems to have kind of a similar architecture behind it. And the first place I actually encountered this was looking at the Raspberry Pi image. It has a driver for loading the firmware, and the driver is called Myriad. So you can get an SDK for this. Theoretically, I don't think just like regular people can download it though. Like I didn't see it available anywhere. I didn't see any actual documentation about this. So we have a Spacepark Vision protocol. It has some data types like status codes and rectangles, tensor shapes. So this would be like the format of an array, like what its shape is. Byte tensor, float tensor, tensor normalizer, load model, unload model, params, entry, image inference, start camera inference. So it's got very high level commands, like start, just like plug the camera directly into the neural net kind of commands. Start camera interface, stop camera interface, get camera state, IMU interface, so it's got an IMU self-test, get firmware info. Here's a bunch of methods, which are basically what we saw out there. Inference result, camera state, firmware info, minor and major version, response. So it doesn't have that much in it, but it's what you would need for a basic TensorFlow inference runtime, it looks like. So that was interesting. And then I got wondering, well, what's on the other end of this? And, well, does anybody know about Spacepark Vision? So, oh gosh, there's a TLD.vision. Yeah, so none of this is going to be relevant. See, this is just going to go into tinfoil hat territory if I'm Googling for Google Spacepark. Yeah, so I don't know where this code name comes from. I don't see it in any other repositories that I know of. This is a binary description of the protocol, which has, again, copies of the same stuff that we were just seeing. That might be useful. I don't know much about protocol buffers. There might be some way to convert that packed description back into a useful description of some sort. It also looks like the protocol is very simple, and there's not that much to reverse engineer if you were into that sort of thing. So then the layers on top of that actually seem to implement, I think this is implementing something. So I don't know if the runtime is actually using TensorFlow at all. It has some kind of tool that I think uses TensorFlow to train and pack the model. But then the runtime, I don't actually know if that's its own thing or not. Cloud speech. Speech recognizer backed by the Google Cloud Speech APIs. So yeah, that's not local. And then drivers, we do have a driver for vision, but actually, is that in here? We're talking to the hat over SPI, but there is a kernel mode driver. So I forget how the kernel mode driver actually communicates to the... Oh, here it is, transport. That's right, it has a weird name. Transport to communicate with the Vision bonnet board. So we're communicating over SPI. And it turns out that this is very similar to something that you might have seen from Intel before. Let's clean up here. There's just too much stuff open. Oh yeah, this was another doodad that another bit of text on the internet that I found referencing Myriad, which is pretty interesting. And this was also something that matches the contents of the Raspberry Pi image. You can find a driver called Myriad, and there is a firmware image in there that actually gets sent over SPI by that driver. And you can even see this helpful traceback here showing those software components we were just looking at. So let's clean up here. Yeah, so we've got a socket transport, which seems to be used possibly for debugging, where Maybe you want to be able to run the Python code on one machine, and then maybe like an emulation of the hardware on another machine. Yeah, so nothing for Spacepark. What do we have? So yeah, we can find some marketing copy for this Myriad, a link to this development kit, but really no actual info. You can see that it has an unspecified RTOS in there, which we'll find a little more out about from some other documentation. There's the product brief describing the development kit. So this is the development kit that Movidius provides, which then Google would have implemented their Spacepark layer on top of. So this talks about the CPU cores as shave and CPU. The shave is also a type of CPU. They're being intentionally vague, but this is a Spark. They're using the Leon core, which is, I think it's an open source hardware Spark core. And then shave is their own thing. It's a very long instruction word core that's designed as basically a shader unit kind of thing for running vectorized code, vectorized floating point. And they have modified versions of, I think, some basic algorithms in OpenCL and like matrix math libraries, for example, to vectorize them and run the inner loops on those shave cores. But then the idea is that your application code that you write on this development kit, most of that runs on that Spark processor. So most of that binary that we're going to see for the firmware is probably Spark code. So yeah, then Movidius actually released this thing, this neural compute stick, which was basically the same processor, but instead of a Raspberry Pi bonnet, it was a USB device. The firmware image they're using on this seems somewhat different, though. So what is the API here like? So we have some C code here. It's talking over USB and doing firmware update over USB. It looks like this is using libUSB, probably. Oh, this is the firmware loader. These MV command files are firmware. But based on the name, I'm assuming that they might actually be some other larger wrapper that's sending perhaps commands to the device. And so maybe we're going to see a wrapper that's like, here's a firmware update packet, and then there's the actual image inside there, and then maybe verification commands or erase commands or something like that. Yeah, so what does the API here look like? I wonder what optimization lists are. So there's like low-level stuff like temperature and firmware. There's load tensor and get result. So this does have some actual kind of high-level neural network kind of stuff in the API. And this is the implementation, which we get as a binary blob. Let's take a look at this. 800 kilobytes. So it's got this MA2X header, DDR init header. So these might be commands in this MV command format. I don't know. We pretty quickly start running into stuff that looks like 32-bit data, or possibly 32-bit code. We've got some strings. Let's take a look at just the strings. Oh, that's interesting. You can see what branch they were on here, and there's a disabled driver derating for DDR. I guess that's what they were working on. Fathom. I think I've seen that code name somewhere, but I don't know what that is. So you can just see some strings that give you some idea of what the structure of their code looks like. So you can see some paths here that show they have subdirectories for the shave, like DSP code, basically, the shader code, and then directories that have Spark code. So this is probably a shave binary, and then separately we'll probably see the Spark binary. A lot of thermal stuff here. I haven't seen anyone run these processors with heat sinks yet. This is matrix math. Artems is the real-time operating system they're using. And they have DOS file system support compiled in here. So the chip does have an SD card driver, I think, or an SD card device built in. I don't know why they have DOS file system support, but I assume maybe it supports like updating or loading or saving data over SD card. And then USB driver. Oh man, I've got a Windows update. That's cool. Some networky type stuff here. Don't know how much of that might be in use. This might just be a list of all the operating system error codes, even for stuff that isn't compiled in. OVDS Artems. Yeah, so this is interesting. It seems like a relatively simple accelerator that's just you know, doing some matrix math on the shave processors and then exposing an API for that over USB in this case. So that's interesting. Yeah, and then I found some more information about this processor. Where was this from? Yeah, this is a presentation from Movidius about their Myriad 2. So they got some cool stuff, including some graphics. They're really gonna push to have these in cameras for doing real-time image processing and photography, which is interesting. So yeah, these vector processors are the shave cores that they're talking about. And this RISC stuff is Artems and the Leon Spark. And then we start to see the shave architecture. So we have DDR, stacked die, on-chip cache. This is interesting. So we have separate register files for, I think for floating point and for two different kinds of integer. Yeah, integer and scalar are, I think, there's a better diagram, I think, that shows the register files in one of these other documents. But yeah, the idea behind very long instruction word is that instead of having some microarchitecture which schedules all the units in your processor, you just have these giant instructions that have a scheduled operation for everything. And then you do all the scheduling on the compiler side. So I don't think it's public, but there is an LLVM backend that compiles to this architecture. And you can see some bits and pieces of the public LLVM code bases refer to this shave architecture, but I don't think the actual target is public if I've At least it hasn't come up in a Google search. I haven't actually gone through and checked all the GitHub or all the Git repos to make sure that I'm not missing something, because I just started looking at this today. But as far as I can tell, the Shave compiler is not public. Nor I don't think I've seen a public disassembler for this either. Computational imaging hardware accelerators. Where were those? I think this is a new thing. I don't think these are... Oh, wow. Okay, no, I just hadn't heard about these. So here's the die photo. A couple slides down. So, wow. So the memory array seems kind of special. I don't know what's up with this. And then here's all the Shave processors. SIP hardware imaging accelerators. And then system on chip, so I guess this is the Leon processor up there. USB 3 core. This is a nice little bit of hardware. So does that mean that the Vision bonnet has an unused USB 3 port on it? Because I think this is the same chip that the Vision bonnet has. Like, I don't think this is a giant semiconductor company with a bunch of different revisions of this die. I think they probably just have one product at this point. I mean, they got bought by Intel, so they can do whatever they want, but like, I think most of this development happened before Intel bought them. Yeah, 3 SPI, USB 3, I2C, I2S, UART, Gigabit Ethernet, and SDIO. Yeah, so we saw the drivers for SD, which is cool. And this might also have network drivers. I don't think I saw enough networky related strings in there that I would assume that it actually has a network driver, but it seems like that's possible, which is pretty cool. And then, wow, so we've got special purpose hardware for all of these image operations, which is great. TSMC is the fab, 28 nanometer process. Well, at least as of 2014, that was the case. I don't know what they're doing with Intel now. This was an older development board. Graph API construction. We were seeing some evidence of that in the firmware for that compute stick firmware, yeah. Depth extraction, low latency interrupts. Yeah, that's cool. And then I also found this paper from some of the researchers who built the LLVM-based compiler for this architecture, which is pretty cool. Oh, I just noticed a comment from Ryan asking if that file was an ELF. That file we were just looking at was not an ELF, but yeah, ELF files are definitely involved in the build process, so I wouldn't be surprised to see ELF section names in that file. Okay, and SD Swartz in the YouTube chat confirms that the AIY voice kit does in fact do everything on the cloud, and it's basically just an ADC and DAC board that attaches to the Raspberry Pi. So yeah, very different amounts of processing here. So this is interesting too. This is going over how the vectorization works, and then here is the diagram that I thought was interesting. This is one Shave processor. AHB? That means something different in ARM world. They have that labeled as a debug configuration port here, which is interesting. Although maybe this is just connected to the main processor's data bus. I don't know. They have some kind of fancy memory arbiter in this processor though, so I think these are all connected to the fancy memory arbiter. So they have integer, scalar, and vector, and then integer, scalar, and vector. So separate instruction units and register files. 128-bit floating point. Or is that 128 registers? That would make more sense if the floats were bigger than 32-bit, but I thought I saw something where, oh, here we go. Yeah, 128-bit vector floats. So float 16 and float 32. So yeah, they're writing a new LLVM backend, which is cool. This is LLVM IR. This is the first time I'm seeing assembly for this architecture. So it looks like we have just tokens that indicate several different concurrent operations and data widths here. I don't quite get what's going on here. Or maybe the parallelism is specified with these operators. I don't think there's a public architecture manual for Shave, but if there was, there might be a link to it in this presentation. Oh yeah, that's not in any public repo, is it? Because this is an LLVM source file. Oh, that's not a website. Oh, all these new TLDs. Oh, geez. Where did the .com come from? Nope. Don't think that class is public. I developed an LLVM target outside of Tree a while ago, and it was annoying. I wonder if it got any better in the meantime. Yeah, okay, so then the other documentation I found that was kind of interesting. So this place, Eyes of Things, it's kind of hard to tell exactly what this is, but I think what they're doing is they make a module based on this Movidius. And so I think they're computer vision researchers. They're making this thing which has this same Myriad 2 chip on it. So some more info about what they're doing video-wise, or what they're expecting video throughput-wise, I guess. And as far as I can tell, what's going on is that these folks are sponsored by like an EU grant that requires them to document what they're doing in great detail. And so as a consequence, they're actually documenting this Movidius chip better than Movidius currently is. So they have some publications like this, Application Processor Description. And this actually describes some of what's actually going on in the Movidius chip, more so than I could find anywhere else. Block level architecture. This is one of the first places I think I actually saw a reference to the Leon core, which is their Spark. So RTOS usage, Shave overview, and this talks about the different register files, compare and move unit, which we saw some allusions to in the LLVM presentation just then. Shave assembler. I have not seen any evidence yet of the existence of a disassembler. I imagine that one would have to exist at some point, but I don't know what it would be called or where it would be at this point. MVlibs, I think, is their library of like accelerated primitives using the Shave processors. Oh yeah, and I have seen references to a simulator, so the simulator almost certainly has a disassembler inside it. RTEMs in the MDK. configuring the memory and the SD card. Multi-core, always on, system on chip, computational imaging, and visual awareness, blah blah blah. So yeah, VLIW text. Two megabytes of on-chip RAM. What does the CMX mean? I saw some indication that it was multi-ported RAM. Five simultaneous cameras. Oh, they label these buses much like ARM does, so I guess AHB and APB probably were actually talking about buses. Oh, the memory array. Does the memory array have a built-in filtering unit? The memory unit here has a little box here marked bicubic. And it would make sense to put the interpolation really close to the memory if you can do that. That's really cool. Power island. So these are areas of the chip that you can turn on and off independently. So you could power on and off individual shave cores, you could power on and off the shared memory array, CPU subsystem. And are these two separate Leon CPUs? There's OS and RT. I have seen references to there being two Leon CPUs, but I don't remember what the distinction there was. CMX Direct Bus is 128 bits wide, as is the Leon AHB. So this makes it look like there's a separate real-time CPU just for setting up pipelines of processing operations on the shave cores, and then a more general purpose CPU. So Artems runs on the CPU marked Leon OS, and this runs the SIP scheduler. Oh wow, and then they both have available shave cores assigned to them. That's not how I would have expected, but that's cool. Or you can turn off the second core. Huh. That's interesting. Cool, there's a Leon manual and the Spark architecture manual. Oh yeah, Movidius Debugger is part of that development kit that normal people can't actually have. Oh, and there's an instruction set manual under NDA and Platform Designer Databook under NDA. Welcome to the stream where we talk about the public info while lamenting lack of public info in certain areas. I mean, we could probably make some efforts at figuring out the instruction set encoding just based on the public info we've seen so far. But that would be a lot of work. grlib. This is a pretty heavy-duty library. Is Leon open source at all? I don't know. What is actually the background of Leon Spark? I don't think it is open. That is... Oh, no, it's dual license now. Oh, that's great. Okay. That's why we're seeing it in this extremely commercial context, as well as I thought it was familiar from open hardware. So yeah, it's GPL'd commercial dual license at this point, which is nice. This particular design is probably using a bunch of other components that are not open though. Booting up. So there's a boot ROM, which supports Flash, or boot over SPI. I think we're booting it over SPI on the Raspberry Pi. But if you wanted a USB device, you'd probably need it to boot off of Flash and then have it present its own USB bootloader. We've been there, shave architecture. This is pretty vague, but these are the hints that would be useful for trying to figure out how the instruction encoding might actually look. It would of course be useful to have a copy of this compiler and assembler, but that's part of the SDK that is under NDA and not actually available, apparently. Anything else? Oh, a memory map. I still don't know what CMX stands for. That's the fast on-die memory, and then this is external DRAM. Yeah, this is cool. Where would we expect the Leon code to live then? In CMX memory, you think? Or way up here at the bottom of DDR. So many caches. Yeah, these kinds of diagrams are also super useful for just giving you an idea of where different memory regions are actually wired up to. Oh, interesting. So each shave has a higher bandwidth local connection to part of the CMX memory. This is a neat architecture. So yeah, here's some other references to the build system showing that they have ELF files as an intermediate format. I was also seeing strings in some of these files indicating there was like a main.elf. Linker scripts, those would be useful to have, but I don't think we have them. A lot of this is just kind of standard startup code stuff, it looks like. But this, like, if we find names of some of these libraries to be important, this might explain what some of them are for. That is interesting that they seem to have separate compiled libraries for each individual shave processor, like with the hard-coded memory regions, maybe. Another reference to the simulator. Movie sim. It says the RTEMS supports TCP/IP here. Just a bunch of stuff about the build system, which I don't actually have, but then you can see some function names, which are kind of useful. So, start shave, wait shaves, reset shave. Memory configuration. SD card driver. Yeah, RTEMS seems to use Unix-style paths. I've been seeing these around also. Driver performance, that's neat. And I'm just talking about initializing it with a DOS file system. So yeah, and then if you go to these, the same folks who wrote this document, the Eyes of Things project, they also have a repository here. They have an Android app, desktop app. They have an MQTT API. So they, it's not extremely useful because this is designed to compile with the development kit that we don't have. But this is the only example I've seen so far, just out on the internet, of code that you would compile against this API if you had it. So, where's something real? Apps. libccv examples. Detecting pedestrians. So we have a linker script. Oh, is this a... doesn't have much in it, but ram start right where we saw it before. Pedestrian. So each of these applications would compile into a full firmware image for the Movidius chip, including images for the 2 Spark processors and all of the Shave processors. Board support stuff for RTEMS, app configuration. This is all very Silicon Vendory looking code with all the big copy-paste comments. RTEMs, SD card. That's neat. So we're creating a separate thread and running the tests on there, it looks like. Also connecting to an access point. SD card mount, run a bunch of computer vision tests, SD card on mount. So I guess it's probably just sticking the input and output files on the card. Acquire matrix file. Yeah. So it does seem like the file system drivers are probably super useful for writing automated tests. And so this doesn't include any shave code. This is just calling into a library. All of this code runs on that main RTEMS, like OS Leon core. SD card example. Creating a file, writing, sync, closing a file, validate the written data, fatal exception handler. Yeah, so we've got some nice examples that are written in the same style as the code we expect to see in the firmware, which is really useful. There's a REST API example. So are these all just examples, or are any of these actually their application? Pulga was one of the names in their other apps directory. This seems to be their stuff. So it's an MQTT server or something, or client. I saw some bits and pieces of shave stuff in the public LLVM, but I didn't see the actual backend in there. So let me know if you see the code, but I didn't see the actual target in there. Wi-Fi thread. Yeah, so this stuff might be useful. This is in the Eyes of Things software repo. So the other thing I thought would be interesting to look at would be the image from the AIY projects site. So this is the one I mentioned earlier. I already closed the tab I downloaded this from, but it's the Raspbian image that you would get in the box with this AIY Vision kit. So let's try extracting that and looking at what's in there too. So I'm actually just going to use 7-zip to extract this, because it extracts file systems pretty easily. The first extract will extract the partitions. So it says type MBR, and I'm actually going to get a FAT partition and a, I think, EXT partition, like EXT3 or something. So I'm going to have FAT and root here. The FAT RPi, this is just used for booting up the Raspberry Pi. So it'll have things like the device trees and the GPU firmware. It's probably not that useful, but it's probably worth having here. The device trees are kind of relevant because that does set up the Vision bonnet is in the device tree on this. And that's how we load the correct driver. So this is everything that was in that FAT file system. That's the, well, a couple of kernels actually. And these are the bootloaders that run on the GPU, if I remember right. And these are device trees. So So actually, yeah, in the config we have right here DT overlay for device tree overlay is Google Vision bonnet Myriad, which isn't in this file system, but we've seen a reference to it now. All right, then we can extract the rest of the file system. So 7-zip thankfully doesn't actually extract like device files and like all the, all the extra like permissions and time and date information. So it's not going to make a mess of your file system. It'll just give you the contents, which is actually what I want right now. And there's a lot of stuff you can dig around in there for. It's still extracting, but inside opt, there was a directory with this AIY source code. What is VC? I don't know what this is. Looks like something Raspberry Pi specific. TV service. I'm actually kind of curious what that is. Oh, video core. This is the Raspberry Pi video core example code. It's the lower level API for the GPU. Although in this case we're using EGL. That's cool, video decoding. Okay, that's kind of useful, but not actually anything new. Regular Raspberry Pis probably have that directory also. And PyGPIO and Minecraft are also pretty normal, but AIY is special in this image. So there is a microcontroller on there also. I don't actually know what kind of microcontroller this is. I think this is separate from the Movidius chip. Let's see what's in this hat flasher. MCU address, Spoke 61, is it on I2C maybe? It is on I2C. So this is separate from the Movidius. The Movidius is on SPI. This is probably just a separate AVR or something. But it's just writing a firmware update to I2C. I assume there's a bootloader on that micro that they aren't giving us code for. Anyone recognize this architecture? I would expect it to be probably AVR or ARM, maybe PIC. Oh, Tuco found a toy over there. Definitely Google code here. BCM 2708. Is that referring to the Raspberry Pi, or is that a separate chip? I don't remember. I think that's the Raspberry. What is KTD 2026? Constant current RGB driver. I2C ARM. So I don't know which of these are actually referring to the local microcontroller and or to the Raspberry Pi, but could this be ARM code? It could be ARM. Let's maybe hold on to this and look at it a little bit. All right, and this is the one from the Vision, or the Intel Vision compute stick or whatever that was called. MVNC API. All right, and then there isn't that much else in this AIY directory. There's data files for the computer vision models. These are binary protocol buffers. So like serialized TensorFlow data, I think. All right, and what else do we have in this Raspberry Pi? A bunch of normal Raspberry Pi stuff. AIY projects Python in the home directory. And Python Assistant SDK. Okay, and there was something good in lib firmware there too. Let's try this. Oh, geez, what was this called again? All right, Myriad. Yes, so Myriad is the name that we saw in the device tree overlay and in dmessage. So just looking for like what Linux driver this is coming from. We even find the source code for the Linux driver. So this is actually the kernel module source code. And it's sitting there in user source. They're actually legally required to give away this source code in some form, so they probably just figured it was less hassle to include it on the disk image. Right, /user source AIY 0.1. Oh, this is some kernel build system thing. So there's a lot of custom kernel code here. There's the PWM driver, GPIO. How does that stuff actually work? Is this sending a command over SPI also? Oh, maybe the GPIO expander is an I2C device. Hey there, Henry. Yeah, so maybe the I2C bus just has like a microcontroller and IO expander and some A to D or something on it, and that's what these drivers are for. I think the driver we actually wanted was in staging for some reason. Yeah, staging / Myriad. So we have one IO control, transact, which is pretty vague. Submit a user transaction. So this is the first mention I saw of the firmware file name there in the kernel, myriad firmware.mv command. Does this actually parse a header? Request firmware. Oh, that's just a kernel API that finds the file. And this just gives us a raw binary blob here. So Vision bonnet rate firmware. Is it just splatting this directly onto the SPI bus? That's kind of cool. So the SPI headers are going to be included in this file. That's kind of neat. So yeah, MV command. It is just commands that you send directly over SPI. What do the other commands look like? Outgoing header, header T. Incoming header. What do those headers look like? Those are the same data type. Header start T. So we have a byte. Oh, this is great. So we have a 1 byte header. Acknowledge is supported. Hey, Tuco. Cool. Let's hold on to that too. And then I think the other piece we want here is firmware. Oh, Tuco, you're gonna hang out with me? Okay, so this is in lib firmware on the Raspberry Pi. And again, this is just Myriad firmware.mv command. All right, so what do we actually have here? So this is much larger. This is 6 megabytes. Probably writing to a few different memory areas at that rate. I feel like the two approaches I'm always faced with are, do I want to understand the container format and go in methodically, like unwrapping all the layers like delicate tissue paper, or do I just like blast right into the middle and try to find some way to line it up? My inclination is kind of the latter right now, because I feel like I could be unwrapping onion layers with tissue paper all day. Or I could just try to find the largest Spark binary and try to line it up somehow. So I think we're going to find that space, what was it called? Oh, spaceport, space vision, space plumbing. Spacepark. Helps if I'm looking at the right firmware. So here's the actual Spacepark firmware. This is the 6 megabyte one that's actually used on the Vision bonnet. Actually, how do these compare side by side, from the strings at least? Oh, you know, I guess this probably has several ELF files in it. All right, DDR init header for MV command, fathom key. That's interesting. If these are actually something we can turn into an ELF file, that would be useful. main.stripped. I think something was referencing main.elf elsewhere in the strings, and so this might actually be the same kind of string up here as this .elf file. A lot of assertion strings here. I was noticing a lot of repetitive code earlier in the hex dump, which seemed like maybe just like really wide VLIW code or lookup tables. Here's a nice Google path there, / depot Google 3. Kokoro dedicated. Borglet. Ah, what is Borglet? I've heard that before. What is blaze out? It would be cool if they open sourced this piece, even if they can't, open source the SDK. They just were probably, there's probably some technical reason why the NDA won't let them release everything that they've done, and it's too much work to actually figure out what they can release and what they can't. So if we could find correspondences here, we could figure out how the command processing is done. We could maybe add our own commands. It'd be cool to build a debugger for this platform. Like run the example code while you have some other process, which is giving you like a sampling profiler or single stepping or periodic stack traces or something like that. Oh man, there's hard-coded stuff in the firmware for their joy detector algorithm example, which is not at all creepy. What is Mognet? I've seen that in this code too. There are faces left after running NMS. Oh no. There are faces left. Knowledge / Cerebra. Yeah, these are the proto buffer files that it would be nice to have a copy of. Oh wait, no, those are the models. We might actually have a copy of that. That's interesting. Oh no, the .proto is the definition. Yeah, I think we're missing the definitions. I don't know. I haven't looked at the code for the tool that generates models from like full-size TensorFlow models. That might have some more protobuffer source in it. Oh, what is this? MTR10 PFH new. we can do WTF traces. Oh, and this definitely has network code. We have NTP support, we have network mbuffers, defaults to time.google, fun, with hard-coded IP addresses even. This is interesting. I wonder if you can ask this thing to do socket I/O in its current configuration. I mean, I wonder if you can attach a network interface at all. I mean, the Vision bonnet doesn't have an exposed network port, but I wonder if it would be a soldering mod to add gigabit network and, or gigabit Ethernet and USB 3 to it. SPI drivers. Oh, here's more Spacepark Vision protocol stuff. C++ function names. Tuco, you chewing on your foot. IMU processor. Oh, is this going to be for like camera stabilization? That sounds fun. Tap detection. Like motion taps. It looks like this might be the basis of a much nicer Raspberry Pi camera. Like you could do stabilization and white balance correction and a bunch of other image processing stuff on here fast. The Raspberry Pi is fast enough to do most of that in CPU, but this might be fun. Oh, debayering. Camera pipeline configuration, IRQs, more tensor stuff. Oh, different kinds of layer activations. Magnet again. Number of shaves used to run gem. What is gem? I assume they're not talking about the old graphical file manager thing. Oh yeah, floating point 16. I think they use that data type for their tensor database, or tensor arrays by default. FP16. CMX block allocator, compute graph. Is this what they mean by DIY? Am I doing it right? Oh, so I should mention that they do have some documentation on just getting your own TensorFlow models running with this. I meant to bring that up. I think I skipped over it. I think it was on their main page here somewhere. So you go to Vision Kit. If you go to all the way to the bottom through all the cardboard and putting the tab A into slot B and all that, then it goes through SSHing into the Raspberry Pi, using the Python scripts, taking pictures. Here we go. At the very bottom, there's a maker's guide with the TensorFlow model compiler. So you have to export a TensorFlow model, run it through this bonnet model compiler, and then something else happens. So I'm assuming that is what converts it to those compiled protocol buffer files that this runtime can load. As far as I can tell, this runtime is not actually using TensorFlow, it's just compatible with TensorFlow. Oh, the model compiler doesn't have a good link here. That's a problem. So then this talks about the supported subset of TensorFlow. Okay, supported common graphs, MobileNet and SqueezeNet, with an input size of 160 by 160. Oh, and then way down here, I can't even tell where I am because of all the scroll jacking. Actually, it's just having all these on one page that's kind of weird, because the sidebar keeps changing, but that's not actually that bad. The scroll bar is just contiguous and huge. That's fine. And then this actually does link to Maker's Guide, which then contains GPIO diagrams and the microcontroller. Okay. And then it disappears for some reason once you get to the bottom. I don't like navigation that moves around on its own, but otherwise this seems useful. Can you program the microcontroller? It doesn't look like you can program the microcontroller. It just looks like they include some firmware for it. So bonnet model compiler. I wonder if this works for anybody. This is a link to the same thing. Yeah, it seems like this is supposed to work, but I don't know where their compiler is right now, and I don't know if there's any source code available for that. Yeah, I don't know where that's supposed to come from. That's a problem. But it's supposed to be TensorFlow compatible. Crash logs. A lot more USB drivers. Some good debug stuff here. So I saw these earlier. I don't know what these are. There's a lot of random stuff in here, right? There's like child safety analysis / economics, oyster population. So I think these are protocol buffer unit tests. I don't know why these are all in here though. Like, this looks like a lot of kind of boilerplate protocol buffer code, but I don't know why it includes like a self-test with a bunch of data files. Maybe it doesn't even include those. Maybe it doesn't even include those files. Those are just leftover file names from the self-tests. These are useful. These match what we saw in the datasheet, or not the datasheet, but like that diagram that someone probably copied from the datasheet. Different power islands. Bus controls, hardware modules. Drivers. Ooh, per module verbosity level. That's cool. What is that actually for? Command line completion. Huh. Wasn't expecting this to have a command line interface. clone stack. If config, huh. I wonder if this thing has a serial port. Artem's shell. Huh. Oh, is that RFS like remote file system? This is like a pretty loaded build. Huh. All right. So are there any file bits in here that we can actually turn directly into an elf? Actually, first of all, I'm curious what binwalk says about this. Paths, right, that's fine. Most of that is not relevant. Nah. So do any of these make sense as addresses? We have this DDR init header, blah 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 .elf. Where's the main? So main.stripped is down here at like 7E20. So all of this stuff is part of that DDR init header. I wonder if they're writing the app into RAM. I guess I was kind of assuming that they might have the Raspberry Pi programming Flash, like if it needed programming, but they might just be dumping it into RAM every time it boots. So DDR init header, maybe this is going into that CMX memory, the on-chip memory. Let's grab that data, or that memory map again. So the DDR itself is at 8, so halfway through the address space. CMX is at 7. Just looking at these structures first, we've got this header before the strings that seems kind of similar. A8. Could any of those be addresses? I don't wanna be meticulously unwrapping the onion right now. I'm guessing this is the name of the segment and the segment, so that would be RO data. But then we have these repeating structures that seem like... What is that, though? Those are not... There's not really an even length. Just some lookup table for RAM initialization, maybe. Then we have text. I'm assuming the 7 might be the length of the string, but there might be some padding involved there. It does seem kind of like I would want to build a loader for this, to put all the chunks of memory in the right locations. So is this the beginning of main.stripped? There's the A8 again, there's a length of F maybe. I'm seeing that 00 for some reason. And then main dot stripped, null, another A8. Like, I'm wondering if they use this for debugging to set some register that indicates what the name of the current thing we're programming is. And then we had an 8A before also, and then F1C, is that a length? And is that a 32-bit aligned chunk of data? Or is this more header stuff? So this is the data segment. Do we know, can we figure out where the data segment starts in RAM? Like, I think the actual beginning of the data segment is somewhere in this neighborhood. I don't know exactly where. Is this big endian or little endian? I just realized I don't even know. Purely big endian. So in that case, and we're expecting this to go into probably CMX memory, or... No, this is still like the DDR shim thing for initializing it. So I'm expecting this to go into CMX memory, but maybe I should go down to the real application. Yeah, I don't know. This is in the real application, but what does this mean? SHV DDR.data. Is that data that goes into DDR RAM? SH shave DDR data. Right. Do any of these look like addresses? I'm trying to get clues about where the alignment is for this chunk of data. I mean, this 8A thing could be part of an address. I don't know. that would indicate we don't. How much memory do we actually have? $128 megabytes is that much. I think that was just past the end of RAM. If so, that doesn't make sense as an address. Okay, let's find something we know is the segment we're interested in, and then try to match up that segment. So I think this is the shaved data segment. So text and lookup tables and whatever else. Okay, and this is shaved text segment. So this stuff is going to be VLIW instructions, which we don't have a disassembler for, which is kind of annoying. Then I think this is, what is this? This could be the main text segment. It's a little hard to tell because it's, the previous thing does not end with a bunch of zeros. But, oh, here we go, lrt.data. What is LRT? Is that the real-time processor? LRT.init, LRT.ro data, LRT.text. So this is going to be not the main OS image, but the OS image for the secondary Spark processor, I think. That's got the 8A again, and now we just have .text. Is this the main text segment? These sure look like these would be RAM addresses if I started them there. 20. Or no, not 2. RAM is at 8. What is it, 2? There's some GPIO and stuff down there. 20DO. Is that anything? No, maybe those aren't addresses. Never mind. Are those instructions? I would expect a lot of this to be code. Why am I getting zeros here? Oh, why so many zeros? Huh. At least the gap between zeros and non-zeros is 32-bit aligned here, for whatever that's worth. I don't know what this is. Does not look compressed. That certainly might be Spark code. I don't know that much about what Spark code looks like. I'm going to try disassembling this in a sec. I just wanted to look for clues about alignment first. I think this is the main binary. Ideally, I could figure out how to unpack this all into some kind of flat address space and then disassemble it. Yeah, so what's up with this? We have a bunch of repeated values here. What's this stuff? This is, I think, the main init and fini section. So these are initializers and finalizers. And I think this is the main operating system binary we're talking about. And this up here was the main operating system data segment. the alignment here. This looks like this might be the beginning of something, but now we got an 8A here. We'd probably answer the alignment question pretty quickly if we just start disassembling some of this. This chunk of code right after the big gap seems like a decent place to start. Yeah, let's just try loading this into IDA as a flat binary. I think IDA is the only interactive disassembler I have here that will work with Spark. Joseph is asking if RTEMS is a real-time operating system. Yeah. Oh, were you asking because they had a separate real-time CPU that doesn't run the OS? Yeah, I mean, it seemed like the separate real-time CPU was dedicated to setting up video pipelines. So like they wanted something that was more dedicated than the main CPU. Okay, so the memory offset here is going to be completely wrong, but we'll just use this as a starting point. And where were we? This is lrt.text. This is maybe the main text segment. This is around 13 DC50. All right, so I think this might be a command right there. But then I'm starting to not know much about what the rest of this is. And some of this is probably code, but I don't know exactly where the code starts. And here's the zeros. Where do the zeros end? Wow, there's a bunch of zeros. This might have been easier to do in a different tool. Or in the, I mean, IDA has a hex dump also. Let's just try right here. That is 161C68. Kinda has code. That does not look like code, as far as I can tell. Right down here. I don't know what this is, but I don't think it's Spark code. It's possible this IDA plugin just will refuse to disassemble an unaligned opcode, but I would expect that not to be the case. I don't know. Man, unwrapping the onion carefully is enticing. So what do we know about the overall command format? Acknowledge, supported. I don't know if these first few characters are special or if they're supposed to be interpreted as headers also. I'm pretty sure this A8 is a command, or a header rather. So A8 is the same as so this is 8, 9A, and then this is 8. That has the reserved bits. Actually, what order is this in? I assumed this would be least significant first. Order. Yeah. So Stack Overflow is full of people saying you shouldn't do that, and GCP is full of macros you can use to figure out what it's like on a particular platform. But when I really just want, like, yes, I know this is detailed, I just want where is the most common answer and what platform that's for. This is just me being frustrated by the way the internet answers questions. these are just the same couple of irrelevant links over and over again. Whatever. I was assuming this was least significant to most significant, but then that leaves these reserved bits up here where they're not both 0. If the order is the other way around, then these two at the bottom are reserved bits. We have acknowledge, master transaction, no data. Yeah, that kind of makes sense if these are starting from the left, most significant. So then in that case, this next one is a transaction ID. And then a CRC, which is the 0 we were seeing. So I was assuming that 1B was a length or something, but I guess it's a transaction ID. So are these first 4 bytes considered to have the same format? So what is 4D? This is 4, and then 8, D, C, and then D. So if that's right, that would be, it is supported, is not valid, does not have data, it is master, it is complete, and then the reserve bits are set. I don't think that makes sense. Did I miss something in the driver where it skips the first 4 bytes? Okay, so write firmware gets the raw firmware file. I don't see it leaving those first 4 bytes. I mean, it's possible those first 2 bytes are in a different format, like the bootloader consumes them specially in some way. Because it doesn't quite make sense as a normal header. Well, let's try maybe making a Python program to unpack it. I mean, do we actually know enough to unpack individual blobs out of this? I'll see if we can at least unpack one of these sections manually, and if it seems like I know how to do it, then I'll write a little Python tool to do that. Okay, so CRC, and then a 32-bit size, though. That's got to be only if the has data flag is set, right? So what's actually going on here? That was the command, which has a transaction ID and a CRC, but no data. And then we immediately launch into a string. The string is null terminated. I mean, it's possible that ASCII characters are going to be ignored because they don't have this ACK bit set. Or because they don't have this ACK bit because they're all under a 128. So maybe they just use ASCII characters as annotations. So maybe this is the equivalent of debug text in the stream. And then here's a command. Do we know what the command is supposed to be, though? What actually identifies the command? I mean, what does it mean to have a command with no data? Let's assume for now that maybe this command is basically a no-op or like a ping. So it will get a reply with this 1B, but then it won't do anything. And then this is like debug text indicating what the name of the file is. And then this is maybe another command, and that's the CRC. And then this 2 is the first data byte there. Does that check out? So 9A in this case would be 1001, 1010. Supported is not set here, which means maybe this is another placeholder. Is supported. I don't know what's going on there. Is supported as 0, but data... I'm wondering if is supported actually means something different, like this is a packet that's designed for something application level. And then again, transaction ID valid is 0, which is also pretty weird, if I'm even reading this right. This doesn't make sense though, because I don't have reserved bits on either side. Yeah, I don't know. And then this could be like, this could be something that is supposed to be 32-bit aligned. I don't know. Could any of these be addresses? Like FC is something that repeats here. I don't know what that is. This is interesting. I mean, some of this might be just data segment stuff. I don't think I know nearly enough to actually unpeel this onion. Like, what about down here? We have A807, which seems kind of command-like, and then .text null. HCO, is this part of the DRAM stub still? Let's see if any of this disassembles. Like starting at like 8C or something. I think the IDA is just refusing to disassemble it if it's unaligned. Oh, did I just crash VMware? I know, I think I might have just told it to suspend accidentally. It's fine. Well, can we identify Spark instructions via some other method and then get this aligned properly? We could use objdump, we could just look at the architecture and try to identify instructions by site, maybe. I think we're off by a byte here. Like, see that? That seems like it should be a 32-bit entity on its own. Or that. So the least efficient way to do that. I don't really need most of that. I just wanted to see if it disassembles with an offset of 1. That's different. I think I'm still off by some. Yeah, maybe, I don't know. Some of these, the alignment might have been better before. It would be nice to know more about how this stuff is actually loaded. Yeah, that was a bad idea. Let's go back to the one we had before without an offset. Key stuck down. So far those A8s seem to be at least 2 byte aligned. That looks pretty lined up right there. This is data segment for some of the shave code. These are probably floating point numbers. And here's strings. Yeah, I wonder, looks like, it's just weird that the only string we're seeing in the RT processor's data segment is this thing about user input. Like, I wonder if that's part of what the RT processor was doing. Heap section. I think this is RO data. Global offset table. That's GOT. This looks an awful lot like Little Endian. Is it possible this is Little Endian? I should try disassembling this with Spark Little Endian. Like, maybe they wanted this to be the same Endianness as the ARM cores on the Raspberry, I don't know. Alright, let's open this. Right? Like, this could be a RAM address if this was Little Endian. If it's Big Endian, it's just a mess that's maybe maybe unaligned, but I think we're aligned properly. There's a .data segment. Alright, where's the main text segment? I should be using a hex editor that actually has full search. that. Looks like the main text segment. Yeah, so let's go to roundabout 13 DC 59. Here's that big gap we saw before. This is still just full of illegal instructions. Like, none of this looks right. It's, oh gosh, IDA's trying. Yeah, it's just, this is just a huge mess now. Let's find some actual code in here. It would be a little easier to do this if I had more of an intuition for what Spark code looks like, but and there's some things we could do along those lines, but I'm still just trying to just stare at this and figure out how the loader works, I think, is my current approach. I wonder if near the end of the file it has an entry point. What is the last section in here? curious what this looks like in InViz, like if we'll be able to visually easily see the difference between the different types of instructions. This blue stuff is strings. You can see the actual strings over there. These data tables have a lot of runs of similar values. And we have different kinds of code here. It's definitely the main application binary. So this is around 164.070. Is that where we were trying to disassemble? I don't even know if it's big endian or little endian at this point. We didn't have any hints in here, did we? Ooh, endianness? Oh, really? Is there a whole section for that? Oh, it's all little endian. Cool. Thanks, documentation. It is atypical for Spark, but it matches all the other processors in the system. All right. So the main application binary should be down here around like 169. Does any of this disassemble properly? Huh, that's a valid looking pointer. These are illegal instructions. That couldn't be right. Is it possible my alignment's still wrong? I'm looking for something where there's an obvious alignment, but not a difference in load commands. So, like there's a wrapper that has a bunch of discrete commands that load data into memory. And within one of those commands, I can be sure that the memory is contiguous. So either I need to understand how those commands work or find a reference that's within the same contiguous chunk as the code I'm looking to try to disassemble. This repetitive stuff is interesting. I don't see another header in here. This goes right from what I'm assuming is code into some repeating structure. And where does this actually repeat? Opening this modal seems to be, like, I think I have to pick one of these two. I can't seem to close it without changing my highlight. That's weird. This looks again like I'm off by 1 byte. Did I try shifting it by a byte and also using little endian mode, or maybe I haven't tried that combination yet. Delete that, but I wanted to not delete the one that I had an offset applied to. Offset by 1 and little endian. I guess I could have just given it a load offset of 3 and that would have been the same thing. Didn't need to make a new file. I mean, what I actually want to do is have everything loaded into memory at the right locations. Until then, this is all just kind of throwaway experimentation rather than analysis I plan on keeping. Let's try going near the end. 5C5. That is still really bad. Alright, I must be doing something wrong here, but I don't know what it is. I was expecting that by now we would at least see some Spark code that seems to be disassembling properly. Look at how much repetition I'm seeing. Like page up and page down, and a bunch of these values don't even change. See that? It's eerie. And this stuff, I'm assuming if I knew Spark, then some of this might actually decode. I mean, it's possible that that MV command layer breaks up these blocks more than I was expecting. Yeah, like what is this? This has got to be code in some kind of repetitive unrolled loop. And it looks like the alignment is fine. I occasionally see hints that look like the alignment is maybe right, and I haven't seen anything that is definitely an indicator that it's wrong. Am I just not looking in the right places for code that disassembles properly? This is .text. So I think this is the load command. I think this is... I'm not confident that the format that we've been given for the headers and that protocol buffer command, like, I don't know that that's the same format the bootloader's using. It might be completely different. So I shouldn't make too many assumptions, but I'm assuming this is some kind of command header, 4 bytes, and then a section name. Could this be a length for the name? I mean, it mostly looks like this is relying on the null terminator. And the 8A, I mean, I think that might be another header. And then this is where I would start to expect to see instructions. I just want to know what Spark code looks like. Wanted the package. Oh, this has been deleted. This is going to be big Indian spark, but let's see what this looks like. What are these 7FF things? Those are calls. These relative calls. Excuse me. Okay. So this is maybe more typical Spark code. It definitely got a lot of stuff that would give you alignment hints. Like these calls especially would just jump out at you, and maybe the comparisons. I wonder if they would have done anything to intentionally modify the instruction set. Seems much more likely that either I'm just missing something, or that there's some kind of loader layer which is modifying this in a way that I'm not seeing. Are these calls? This looks like Little Indian. Does this work? Really? Is that not code? Are you sure that's not code? That looks like Little Indian Spark. Are we sure this is still set to Little Indian Spark? Is Spark L actually Little Indian? I assumed that the Spark L and Spark B were Little and Big Indian Spark. I wonder if this just doesn't work for Little Indian Spark. I don't know what I would be missing here. That's another call. These are properly lined. Okay. Really? What? Yeah, I don't know if that's supposed to be code. I mean, I don't know if any of this is supposed to be code, but it's like you just throw a dart into the middle of this file. Most of it's going to be Spark code. Not disassembling, though. Oh, there isn't any public info on this bootloader, is there? I assume that's in the SDK, which we don't have. Did this have, I mean, we've been here, but did this have something about the bootloader? Oh, this claims that there's a secure boot mode. I don't see any signs that we're using that. Single vector trapping. They've got JTAG. That's neat. Yeah, movie convert is what we need, I guess, to make the boot image. We can probably find this exact table in the data segment. Yeah, so nothing specific on how it boots. I don't know. I don't know about this code. Did we disassemble some of these instructions correctly? I just haven't seen any evidence so far that this is set up right at all. We had some call instructions. See, that looks like it's decoding for big endian. I'm wondering if maybe the little endian Spark disassembler in this version of IDA just doesn't work. Let's maybe find a different Spark disassembler. I think... Oh, how many cross compilers can I get at a homebrew? I might need to compile objdump myself. This, I wasn't even searching for Movidia stuff, and Shave comes up again. I don't think any of this LLVM stuff that's public is useful, but we might find some bits and pieces. I think it's just driver level stuff, like compiler driver. Oh, yeah. Do we need any other prereqs to compile just objdump? I don't think let's just find out. Let's just grab the source to objdump. So it's part of binutils. I think we just want to grab the latest binutils release. Oh, this cat is so peaceful. Oh yeah, can we use capstone on Spark Little Endian? I'm also really tempted just to byte swap the entire file and then feed it into IDA. Actually, that's a terrible hack, but I'm kind of curious. Let's try that. Yeah, Yep. This is going to be terrible. Sure. So I'm going to tell it Spark Big Endian this time since I byte swapped the file. As far as I know, Spark Little Endian might not actually work, but it is still quite possible I'm just doing something unrelatedly incorrect. These seem like they're 2 bytes off. Oh wait, no they're not. My hex view is just centered weirdly. This is actually aligned. Okay. Are these calls? Oh! Look at that code. That looks like code. So yeah, I think Spark Little Endian is just broken in this version of IDA. This is looking right. Where's the beginning? Let's try to find whatever's right after that big empty space. So let's see if we can start disassembling around here. This is like 163. Is it code? Is it code? Maybe. That looks code-like. Yeah. The addresses are still definitely wrong, but this is code, and it is Little Indian Spark, and it is disassembling now. Can we find a load address for this? So what about the stuff before the 0? Before this big 0 region, is that also code? What about that? That was a reference. Is that the text segment right there? XET dot. Is any of this stuff code? Maybe. Seems unlikely. I think that was the segment name, so it couldn't be before that. Could that be an address? These 8.1 areas. How much is that? That's oh wait, that's what, 16 megabytes? That could make sense if that's like 16 and you know, maybe 20 megabytes past the beginning of RAM. This is inside my segment though, so I mean, I don't think this has anything to do with the loader. I think this might be initialization code that's like clearing memory or something. I don't think this is where my text segment would be. Could it be something around there? I mean, 8A seemed like more of a command. This could be an address. 8000A010. This is byte swap, so we're looking at it in big endian now, even though it's actually little endian. Like, what if this was a load address? This was like a size? Or was this a size? Or is this another address? A610. And is this finally the contents? So is this code at C76? Probably not. I'm expecting addresses to be aligned here, but I don't really know. It is certainly possible that the alignment is just changing every time we switch segments here, because the SPI protocol has no reason to be aligned to a 4-byte boundary or a 16-byte boundary or anything like that. It's natural for that to be byte-based. Strings look especially strange after going through the byte swapper. I wonder if anybody's already done reverse engineering tools for that MV command format, because that would be the next thing to do. I don't know if we want to go any further. This is just kind of an idle curiosity, but if we wanted to dig further into this, then the first tool would probably be something that converts an MV command into a pile of ELF files, or even just one big ELF file. Somebody's like, give me info, and they're like, yeah, so that's all just loader stuff. In fact, even just searching for this gives us less information than I would expect, maybe. Because there are actually some other references to that. But anyway, I think that's about a good stopping point for this. I just wanted to see what we could see, and it looks like there's a bunch of Spark code in there, which I don't have great tools for disassembling right now, but we could theoretically disassemble this. And it looks like it's a combination of a bunch of stuff from that Movidius SDK and some Google code which implements their protocol buffers, what was that called? Spacepark, yeah, Google Spacepark. So yeah, I would like to do some more disassembly using Binary Ninja. Binary Ninja doesn't do Spark, so if anybody has a favorite Spark disassembler that might be interesting to try with this, I'll have to check. It looks like Capstone supports Spark. I assume maybe Radare would support Spark. Yeah. Is there an Endian selector here? This seems like it'll work. This might be something to try in the future. Anyway, I hope some of that was interesting. I'm gonna wrap this up, but I'll see folks soon. I'll get back to editing videos, and let me know if there are specific things you'd like me to try, particular projects you'd like to see more of or less of, and I'll try to take all that into account. And the next video I'm working on is more of a kind of status slash, to be honest, I haven't really figured out what the storyline for this video is, which is part of why I've been dragging my feet on it, but basically another update on the Tuco Flyer and related progress. So yeah, I'll have that edited out as soon as I can get it, and in the meantime, we'll be doing random streams when they come up. I don't currently have a schedule for streams, but I'll try to do it when I have something interesting, and I'll try to keep folks posted. Thanks a lot, everyone. Happy hacking. And a special thanks to everyone who supports the channel. It's really great when you send links to your friends, when you send in stuff to take apart, or when you send a couple of bucks my way to help me pay the shop rent. And that's how we can keep doing this, and let me know how I can help just make it as good of an experience for everyone. And I'll just keep trying to do this. I'll see you all later.